So welcome back to the next lecture, lecture number 3, unit 1, photometric image formation. What is meant by image formation? The last class we had a small introduction to geometric primitives and transformations. Image transformations. Today we will be learning how an image is formed in a camera, or how photometric images are being generated. Okay, we'll not see in depth, we'll just understand the basics of image formation based upon optical theory, how light is capable of making images. What do we mean by photometric image formation? Photometric image formation means the process through which an image is being generated from a scene. The lighting conditions, the scene geometry. We have seen the geometrical perspectives in the previous session. The surface properties, camera optics, and how all these things will interact to produce a clearly viewable image. Okay, so this is the foundation for today's lecture. Photometric image formation. What does it mean? It means that this is surroundings, the environment where we are going to take the photograph, the scene, the depth, the color, the lighting, the surface, and all these things, how all these things put together is capable of creating a digital image. So what are the components of a photometric image? What are the important components? The important components are, number 1, radiometry. So these are the important domains that you have to keep in your mind, or important verticals that you have to keep in your mind when you are working with photometric images. When you are trying to create an image, these are the important things that you have to keep in mind. First one is about the radiometry, how the light is a optical wave, right? Can be considered as an electromagnetic wave also. Light has infinite properties, very, very interesting properties. Do you know how far is Earth from Sun? From Earth, how long or how much far is Sun? Is it not the wonder of God to bring sunlight to Earth, and even much beyond that? Without sunlight, of course, we all cannot live, right? Sunlight is here, it is giving life to plants, it is giving life to all the other animals, and these optical waves which are generated thousands of light years away from Earth, but still you can see, you can feel the power and heat of sunlight. So basically, it's a very interesting phenomena that we are going to study. We are going to study about how light interacts with various surfaces. So first part, we should study the radiometry, different surroundings, the environment, and how light is going to get reflected, diffracted, and so many other phenomena there. We'll be seeing that as we go on. all these things would lead to image formation. Optics. Of course, you should know, see, every photo will be having, or every image will be having an object, right? So how we can focus the object? The optics part deals with all these kind of mechanisms. The mechanism by which light is projected through a lens onto a sensor plane. Finally, the sensor. See, through light, you can know that we have shadow, we have light being reflected, we are able to create or form the image. But this image has to be digitally stored somewhere, right? Has to be saved. For that, we need sensing, and we'll be doing some kind of editing and other aspects also. The conversion of continuous color images into discrete digital samples, often factorization of noise and sampling deficiencies. You know, basically, all the image formats what we are using, whether it is PNG, JPJ, all these things are a kind of compression techniques. The image is stored as a particular format, and whenever you open that, the format is being done in a different, is readable, is created back into the original, the way it was taken. So it's all multimedia compression techniques, or it's multimedia storing techniques, in fact. Not just compression. Compression is a part of that. It is all how you store or save this image. That is what is the format. You have, we might be very familiar with PNG, right? PNG, JPJ, JPEJ, and so on. Okay, all these things are particularly defined formats, defined for storing images. So, in a way, the image is also compressed. Okay, so these are the important components of photometric image formation. See, every of my slide, mostly 99.9%, is an answer to a question. So what are the components of photometric image formation? You can explain this and you can write this. We look into the important aspects as we go on. So radiometry, or in other words, lighting sources. So different lighting sources. Point light source. Okay, so you have a small point, and from that you have a light source that is emerging. And in a photometric image, what happens is that based upon the light source, you get an image. How it is being defined. Okay, so a point light source has specific intensity and color spectrum. For a distant source, for example, I told you about sun, rays are modeled as parallel. It's parallel. From all the angles you get the light. Okay. Intensity generally falls off with the square of the distance from the source. Always, this is a very interesting thing. It is inversely proportional to the square of the distance between the light source and the object. Area light sources. Finite areas. It's a limited area, like you say, have flashlight or something like that, or fluorescent ceiling fixtures. These shadows are not very sharp. They are soft shadows. Okay. You know what is umbra and penumbra? You might have read it in your basic physics. So you won't have any sharp shadows. You will be having a variation in intensity of the formed images or shadows. Next type is environment maps, a representation mapping incident direction to the color values, effectively assuming all sources are at N. Okay, so these are the basic lighting sources. This deals with the radiometry. So next, we'll have four important points about reflectance and shading models. So what are the reflectance and shading models? Okay, here we are going to see four different models in detail. The first one is called as bidirectional reflectance distribution function, BRDF. This is the most common model. Here we'll be describing the amount of light or the number of photons in other ways that fall on the particular object from the incident direction that is emitted in a reflected direction with reference to the normal to the surface. In the previous class, I told you about a plane. We have a normal and so on, right? You remember that? So here, what we'll do, see, all these things are extremely important because we'll be studying different dimensions of an image and how we are going to transform the image, how we are going to interpret meanings from the image. Okay, so here, as stated, this is the most general model describing how much light from an incident direction is emitted in a reflected direction relative to the surface normal. Yes? Any queries? Next is a very common diffuse Lambertian reflection. What is meant by scattering of light? I'll ask you a very basic question. Can anybody tell me why sky is blue in color? Can any one of you tell me why sky is blue in color? So take this as an assignment question. I'll post this in your announcements also, and then so that you give it to me in writing, maybe by the next class. Okay? So that now all these concepts are basically to make you understand scattering of light. Okay? So diffuse reflection, where the scattering is uniform in all directions. So, according to Lambert's cosine law, the brightness of a diffuse patch is proportional to the cosine of the angle between the light source and the surface normal. So now these two figures really explain what happens when light is hit on a surface. So at an angle, see, this red line is the incident angle or incident ray. It hits, it gets scattered. Okay, so this particular image or this particular diagram represents how light is scattered. Now, bidirectional reflectance distribution functions or BRDF is parameterized by the angle. See, this is the incident angle VI. This is a reflected angle VR. Both these things are, you may note that both these things are vectors. Okay. The light ray directions make with the local surface coordinate the frame, that is this one, dy, dx and the normal L. So here in this particular section what we are studying is that we are studying the reflectance and shadowing models. What are the different kinds of reflection phenomena, scattering phenomena that is happening when a light hits a surface. We have 4 models that we need to study. First one is the BDRF, which we are seeing now. Sorry, BRDF, which we are seeing now. The second one is a diffuse model, the Gaussian model. The third and fourth one will be coming in the next slide. Specular reflection, Phong shading. So the other 2 reflectance and shadowing models, shading models, specular reflection, which means that depending upon the angle at which the light is incident, there is a change. The way the objects look, make different shapes. So this type is called as specular reflection. And combining all the first 3, we get Phong shading. So heuristic model that combines ambient, diffuse and specular components into a single equation to simulate realistic surface appearance. So here we have the graphical representation of the component values as a function of angle away from the surface normal. Okay. So here we are depicting the polar plot as well as the component values of the function of the angle. So reflectance and shading models are done. And now we look into the optical effects and different lenses. We begin with thin lens model. So in optical effects and lenses, what we'll be studying, we will be studying the first. Yes. So we have a single piece of glass with very low equal curvature on both the sides. This is called as thin lens model. So here we'll see what these things, these numbers mean. But for the time being, you can please note that you have F as 100 mm. Okay. Zi, whenever there is a suffix I, it stands for incidence. ZO, output, or the reflected one. So please make note of these quantities. F 100 mm, Zi 102 mm, ZO 5 mm. Okay. And there is a quantity called as D. So let's consider the object, the relationship between the distance to an object z0. The object is known by z0, and the distance between the lengths at which a focused image is formed, that is zi, can be expressed as 1 by z0 plus 1 by zi is equal to 1 by f, where f is the focal length of the lens. So after thin lens model, next is about the depth variation. The allowable depth variation in the scene. See, what do you mean by depth? In a photometric image, what is meant by depth? A three-dimensional. See, there are two things, na? Front in the front and the other one in the back. There is a distance between these two objects, right? So this is represented by the depth. You have a third angle in a 2D photometric image. Okay. The depth variations in the scene that limit the circle of confusion to an acceptable number is commonly called as depth of the field and is a function of both focus distance and the aperture as shown diagrammatically by many lens markings. So you have, whenever those who are very much interested in photography might have used this kind of camera, and you have that variation shown in the diagram about the depth variations. Okay, depends upon the size of the image that you are taking. Initially, the first thing what we learned about was a thin lens. Now, it's about the depth variation. In thin lens, the size or the height of the object is being calculated. Here, we are finding out the depth of the portions within the image. So the depth variation depends upon only two factors. One is the focal length f and the aperture diameter. When I was showing you the thin lens, I showed you that d, no? The quantity of d. That is the aperture. Say, if suppose this is the line, this one is d. F by D, F is the focal length and D is the diameter, aperture diameter. Depth variation is denoted by this quantity N or F has. So another one important concept called as vigneting. What is vigneting? So what is vigneting? So vigneting means the property of the light to fall towards the edge of an image. Okay. The tendency for the brightness of the image to fall towards the edge of the image. So what will happen? We have two types. One is called as natural vignetting and the other one is mechanical vignetting. I will explain all these concepts very clearly again with respective images as I told in the next class, as I told in the previous class. Next class or in the upcoming classes, I will be posting it separately. Is that okay? This subject or this course is a theory come practical course. So when we do the practicals, I will just try to explain to you what all these concepts mean like. Okay, we can work on many examples. So your practical sessions, you will be learning OpenCV. OpenCV is a Python library that is used for computer vision. This course is extremely valuable to you. As much as it is valuable, it is so much difficult also. So, vignetting, what is vignetting? We'll be learning in detail as we go on, but the basics and for the exams, you got the point is what I believe. So, digital sensing pipeline. A world or an environment is a place where is a scene which you wanted to record digitally. So what are the things that is required for digital sensing of scenes or images? So we have photonic sensors like CMOS, charge coupled devices, which is going to it is going to digitize your image. Whenever a light falls on the device, that is being recorded. Okay, so it converts photons into digital bits. So another consideration what we have while digital sensing is about the noise and sensitivity. So most of the photographs or most of the images that is being recorded will have some kind of variations in light. You will not be able to view images as clearly as you see it with your eyes. It is not the case with audio files. You find that the noise is much less in audio than in images, in camera recordings. Okay. So the electronic gain is controlled by ISO setting. So concluding today's class, the last two important things is about color filter arrays or CFA that samples green at twice. You might find that most of the images, blank things you have background as green. Okay. So why do you have that? Because green at twice the density of red and blue. The missing values are interpolated via demosaic. Okay, base pattern. The final thing in the sensing pipeline is about the gamma correction. So in digital sensing pipeline, I mean that the stages or the things that is being required for digital sensing of the world or the scene. Okay. So with this, I conclude today's session, lecture 3, unit 1, computer vision. Let me have a basic summary of what we have done today. We have understood what is photometric imaging, right? And then what is the next thing we have seen? What is the next thing we have seen? We have seen thin lens model. We have seen depth variations. We have seen, finally, we have seen the digital sensing pipeline. So thank you all. Thank you for listening to me. Thank you very much.